Section 3.3 starts with a topic that you are very familiar with. You've been doing it since probably, at the very least, Algebra 2 in high school. The reason I'm referencing that is because I have a daughter who's working on some increasing, decreasing concepts right now. But the idea of increasing, decreasing, of course, is something you've known for a lot longer. We're going to start out by giving it some real rigid definitions. And they're going to sound a little bit funny, but bear with me while I draw you a picture for each. So the first one is increasing. An increasing function is a function on an interval where it has the condition that x1 less than x2 implies that f of x1 is less than f of x2. And, of course, the image would be something like this. So it says that x1 is less than x2. So those are x values that are in order from left to right. And that the y value that corresponds to x1 is lower than the y value that corresponds to x2. So there's f of x1 and, roughly speaking, f of x2. It is a function, so we have to make sure that it's passing the vertical line test. That's not something we tend to concern ourselves with or see much problems with at this point. But really doesn't matter what happens in between. So I just sort of connected the dots, and I did it in a way that was a curvature. But it could dip down. It could have lots of, things like this in between. It doesn't make any difference. All right, so if we're talking about the fact that the function is increasing, though, between x1 and x2, for it to increase between the entire interval, it needs to be going uphill for the entire interval. Okay, so we can have graphs that are doing lots of things between certain values, but if we're identifying a certain interval as increasing, then the entire way between x1 and x2, this is the image we have. And likewise, on decreasing, the only thing that you see different is that the f of x1 is greater than f of x2. So again, image-wise, the x1 and x2 are sort of in order. We're not changing those orders. We're just changing what happens on their y values. So instead on this one, the x1 has a y value that's higher than than x2's y value at f of x2. And so decreasing means that between those 2 points, it's going downhill. And this idea of uphill and downhill in sort of a graphical perspective is something that you're very familiar with, looking at a graph and just saying, oh, look, it's going down. Oh, look, it's going up. And we read graphs from left to right just like we read our English. So if you take a look back, though, at the title for our section, it actually talks about more than just increasing and decreasing. It talks about this thing called the first derivative test. So there's a relationship between a function being increasing or decreasing and what happens to the graph's derivative. And specifically, it's the first derivative that we're talking about. And you might be like, okay, but we've just been talking about derivatives, so what are you getting to? Well, when we get to section 3.4, we're going to be talking about the second derivative, which we've mentioned. And there's a different relationship when we get to that kind of derivative. So for right now, we are talking about a first derivative. So if you take a look here, this is, in fact, the relationship. So we're going to suppose that we have a continuous function on the interval I. That's why we're connecting them, so to speak, connecting the dots like I mentioned earlier. And if, in fact, the derivative is positive, then we can say that the function is increasing. And if the derivative is negative, that's number 2, then the function's decreasing. And if the derivative is 0, then the function on an interval, if it's 0 on an interval, then the function is constant. Okay, so now think about what that means in terms of this picture over here. Let me draw in just the increasing one that I had before. Looks something like this, right? Just roughly speaking. If I were to draw tangent lines at any of the points on this graph, they would be going uphill, right? Just because the graph's going uphill, right? I mean, yeah. And when we're looking at that orange line, what can you tell me about the slope? Is it positive or negative or 0? It's positive. But that slope, that tangent line, is representing what the derivative is doing. So the fact is, at all those points, I can draw orange lines, all of them, that have positive slopes. So a positive slope means that the derivative is positive, so I have an increasing graph. And likewise, if I had drawn the other graph instead, if I had drawn this graph and I were using any of those points, and I'll do green lines on this one, and I were to draw this tangent line, at every place that I draw a tangent line, I have a negative slope, right? And so this idea of a negative slope or a negative derivative directly happens when in fact I have a decreasing graph. And if I were to have a constant graph means that it's horizontal line. Okay, that's what a constant graph is on an interval. And every tangent line that I would draw would of course be, this looks terrible, but it would be the same line itself, right? So that line I drew that was red has a slope of 0. So I've got a constant graph and vice versa. So the first derivative test is one step further, and it goes on to say, let's suppose that we have a continuous function on an interval, and we have one point that's called a critical number. And we talked about this idea of critical numbers before. Critical numbers are places where the derivatives are either 0 or they don't exist, okay? If we have a function that goes from having a positive derivative, right here, to having a negative derivative, i.e. the graph is changing from increasing to decreasing, so it's going from up to down, then what we say happens at this point in between is that we have what's called a local maximum. We'll also call it a relative maximum. I talked about this already a little bit when we did section 3.1. This idea of having something where there's a peak or a valley. So when the slope goes from positive to negative, right, that's the slopes, the derivatives going from positive to negative, I end up with a local maximum. And if I reverse that and the slopes go from negative to positive, right, they go from decreasing to increasing, then this location right here would be a local or relative minimum. And again, that's my negative slopes to positive slopes. And if in fact I do not have a change in my signs, and I drew this one before and I told you we'd talk more about it later. This place right here is a critical point, right? It has like if I set it equal to 0 and solve on the derivative and all anything, I get this particular value. But the reality is that this slope's positive and this slope's positive. It's increasing and it's increasing again. Then I have no relative or local extrema. It just doesn't happen there. It's still a critical number because it still has a derivative of 0. It just doesn't end up producing a local or relative extreme point. So what we're going to do next is we're going to actually take a look at figuring out if functions are increasing or decreasing, and then eventually if they have maximums or minimums. So we're going to work with some functions, again, that are not near as messy as ones we've seen before, so that's really good. But they're not always even polynomials either, right? The reality is that if you were doing this same lesson for parabolas, you would be in an Algebra 2 class. My daughter's struggling a little bit with the whole idea of increasing and decreasing right now in her Algebra 2 class. And they're doing it based on finding vertices. Right? Do you remember that from parabolas? Mm-hmm. You do the parabola, you find the vertices, say, oh, look, since the parabola is opening downward and the vertices here, the increasing part's this, that's what they're doing. So we're not working with just parabolas. You already have a tool that allows you to do that in a sufficient way. The whole point of calculus is to go beyond where the parabolas end, right? What else can I do with this? How else can I find these relative extreme points? So if we're taking a look at this function, we see one that's not a polynomial this time. I actually have a rational function. I mean, we could combine them into a single expression, but there's no need to either. Our goal, as we're working through all of these, is to find where the derivative is actually equal to 0 and see what happens on either side of it, or in between the pieces if there's more than two sides. So we will always find the derivative when we're working with finding increasing or decreasing. So anytime things talk about increasing, decreasing, or maxes and mins, that should be a red flag. I need to take the derivative, set it equal to 0, and see what happens next. So we're going to take this derivative. So what's the derivative of x? 1. This piece right here would be a lot easier if I wrote it this way, so I'm going to do that. What's the derivative of 4x to the negative 1?
Negative 4x over 4x.
Negative 4x to the negative 2, and then I'll change it. Thank you, Kaylee. Yeah, so negative 4, right, the negative comes down, and then decrease the negative 1 by 1 gives me negative 2. And then Kaylee was actually already moving ahead to simplifying, which is wonderful, and it would simplify like this, which is definitely useful for what we're doing because our whole goal is to set this equal to 0 and to solve it, and it's a lot friendlier to see my exponents positive when I'm trying to solve things. Negative exponents just mess with our brains, okay? So if you're trying to solve this, what might you do next? Say again? Move the 1 over. All right, so we can have negative 4 over x squared equals negative 1. Cool. What's next? Okay. Let me, sure, why not? It's not what I was expecting you to say, but that's okay. We can do it. Okay, so Callie said to multiply by negative 1/4. You're trying to get x alone. There's a tricky thing that's going to happen on this one, but let's start with this. That'll work. So I end up with 1 over x squared equals 1/4. Is everybody good at that? Her goal was to get this 4 to cancel out. It's a little non-conventional. That's why when she said it, I was like, oh, that's not where I was expecting to go. But you could. It doesn't hurt anything. You could. We need to get rid of the negative one way or another, right? Okay. So there's several ways to solve this for x, all right? We do need to be a little bit careful as we're working because there's something we're going to have to come back to in a minute here to make ourselves aware. But at some point along the way, whether you do the 1/4 like Kaylee just said, or whether you do this step that I'm about to do in a minute earlier, you're probably going to cross multiply, right? It would be friendly to not have the denominator. Or if you prefer, you're just going to multiply both sides by x squared. That's fine too. And the point where we are right now, cross multiplying. So I'm going to have 4, oops, I don't know why I changed to purple. 4 is equal to x squared. Okay? And you're going to take a square root at some point as well. So what does x equal here? Plus or minus 2. Good job remembering the plus or the minus. However, this is the location where the derivative is equal to 0. The reality is that you have critical numbers when things are equal to 0 and also when they don't exist, right? Where does this function, the derivative, 1 minus 4 over x squared, not have a value? At x equals to 0, right? The fact is that there really is a denominator that sort of disappeared when I cross multiplied, and I still can't have x is equal to 0. Whether I cross multiply or not, x is equal to 0 is not allowed. All right, so I have another critical number from right here when I have 1 minus 4 over x squared equals to does not exist. This happens at x equals 0. So there are actually 3 critical numbers. That's what I was talking about in terms of being careful. 3 critical numbers. All right, so what are we going to do about these 3 critical numbers? Well, they separate my locations into 4 different spots. So if you think from a number line point of view, and you have to mark them, of course, in order. I've got negative 2, I've got 0, and I've got 2. There are 4 intervals in and around those particular x values, right? It separates my number line into 4 locations. Okay, is that good for everybody? Do you understand where I'm getting those 4 spots? Okay. What we want to do is we want to figure out what happens on those intervals because the reality is we picked these 3 points. We found these 3 points. We didn't pick them. We found these 3 points because these are the 3 places where the graph has the potential for changing from increasing to decreasing or decreasing to increasing. But on each individual interval, it's doing one thing or the other. There's no changes. There will be no changes to the left side of negative 2. It's not possible. Okay, that's what the first derivative test tells us, is that it's going to be solidly one thing or another before x equals to negative 2, and between negative 2 and 0, between 0 and 2, and then after 2. Okay? So here's the cool thing about that. Because it has to do the same thing on this entire interval, I can pick any point in that interval, and it can serve as a test point. So what I'd like to suggest, is that we take the point negative 3. And if you don't like negative 3, take another point, like negative 4. Negative 10, I don't care, just pick one. What we're wanting to do is we're wanting to figure out what does the derivative do at that location. Whoops. Okay, so this is the equation that I'm trying to plug the values into. Okay, the one that's boxed in this bright yellow. I'm not going to write with the bright yellow, I promise. Okay, but the boxed in part. If I plug in the number -3 into x in that derivative equation, do I get a positive? Do I get a negative? That's what I'm questioning. It's going to be one or the other. Has to be. So if I plug in -3, I'll have -3 squared, which is 9, and that means I have 4 over 9, right? And when I do 1 minus 4/9, will that number be positive or will that number be negative? It'll be positive. So on my number line, what I'm going to do is I'm just going to put a positive. I got a positive number. I don't care that I get 5/9. It's completely irrelevant. I mean, I chose the -3. What if you chose -10? It doesn't matter. We're both going to get positive. Even if we get different values, both going to get positive. Typically speaking, there are some nice numbers that we do often like to choose. Ones and negative ones and zeros are wonderful things to choose when we have the opportunity. So choosing a -1 in between -2 and 0 is a very nice choice. So in some sense, let me write down what we just did a minute ago. We actually found that f prime of -3 is positive. And the next thing we're going to find is f prime of -1. It has just as much likely chance, depending on what functions you're working with and so forth, to be positive or negative. So you cannot make an assumption based on the previous value. The -3 that we just used has no bearing. It doesn't have no bearing, but it has little bearing on what happens next. It's all based on the function itself. So if I put in -1 here, so what is -1 squared? 1, and then 4 over 1 would be 4, and then 1 minus 4 would end up giving me a negative number. So this one's negative, and on my number line I'm going to put a negative. Okay? All right. Well, if I chose -1, choosing 1 should be quite friendly as well. So if I do f prime of 1, the reality is this particular derivative was x squared, right? So every time I squared the -3 or the -1, the negative wasn't there anymore. You'll know what I'm talking about, right? So if I put in the number 1, I'm going to get the same thing I got as when I put in the -1 on this particular function. So if I put in 1, I have 1 squared is 1, 4 over 1 is 4, and then 1 minus 4 would be a negative, right? So we get another negative here. So this piece is negative. And then we might as well just use the same 3 that I used the -3 for before, because this has some really nice symmetry on this particular one. And if I put in 3, I'll end up getting the same thing I got when I did -3. So it's positive. Okay? Now the question actually asked me to identify the open intervals where it's increasing or decreasing. So when it comes time to do my answer, I need to make sure that I'm doing what I'm asked to do. Let me make all of this a little bit smaller, in fact. All right. So we're going to identify where is this function increasing. So which pieces of my sign chart, the positives or the negatives, are the increasing ones? What was that? Okay, so it's the outer edges, right? The positive signs. The pieces of my graphs that are increasing are over here and here because they're where they put the plus signs, right? It's where I got positive derivative values. So when I'm looking at identifying the intervals for increasing and decreasing, they're the intervals that are going to incorporate the -3 and the +3. In particular, though, they're the intervals from -infinity to -3, union 3 to infinity. So we're asked to decide for it in terms of open intervals. So if you remember, this is interval notation. If it's something that you haven't seen in a while or need some brushing up on, might be a place to come talk to me one-on-one or go to the Success Center and ask them to remind you. But what we're doing from a number line perspective is we're starting from the left-hand side of the number line, which is -infinity, all the way until, I didn't mean 3s, they're 2s, aren't they? Is that what you're going to tell me, Nick? Yeah. Yeah, they're supposed to be 2s. I got carried away with the 3s that we were talking about a minute ago. Thank you. Yeah, so all the way until we get to -2, and then I stop increasing because I've got some negatives in here, and then I get from 2 to infinity. Sorry about that. Yeah. Please make sure they get fixed. And then the other piece was supposed to be identifying where it's decreasing. Okay. It'd be really tempting to say that it's decreasing from -2 to 2. It's not -1 to 1 either. There's a problem. Yeah. Do you remember how we had the 0 in the middle? What's really happening on this graph is there's an asymptote there. All right, so the graph is not increasing or decreasing at the asymptote. It doesn't exist at all. So when we're writing the interval notation, it really has to not include the places where it was 0 or doesn't exist. So this graph is actually decreasing from -2 to 0, and then from 0 to 2. And what you'll notice that I'm using here as well is I'm using parentheses everywhere. There's a couple of reasons for that. Reason number one is that if I've got a -infinity or an infinity, those are values you cannot have, equal to. Those aren't values. They're concepts, really, right? They're giving us this idea of something going on forever. The other reason is because a function is not increasing or decreasing at a specific point in time. It's always increasing or decreasing by our definitions on an interval of locations. So we wouldn't say it's increasing or decreasing at 2, right? We don't put those brackets there. And for some, at least at some portion of it, the reason that makes sense is because it was actually 0 or does not exist at that point anyway. And then it also talked about the fact that these are open intervals up here. So lots of reasons to sort of remember and use back on the fact that we're using parentheses and not brackets. Okay, that's it. That's our answer. Any questions on that process? So our goal, again, to remind you, is to set things equal to 0, doesn't exist, just like we were doing before, but then to use test points between those values to decide if I get positive or negative values for the derivative. All right, let's try it again, this time with some trig. My function is f of x equals cosine squared of x minus cosine x. And I do have an interval from 0 to 2 pi. You'll often see that kind of an interval when we're working with trig functions. Everybody likes to use, 0 to 2 pi, 0 to pi, maybe -2 pi to 2 pi, depending on what the problem is. But those are common values. All right, so to start with, what do? A derivative. You bet. All right, so we had a derivative kind of similar to cosine squared as a function on our test. And when we have cosine squared, it's a chain rule, because the cosine is being squared. So the first thing we did is we brought the 2 down, rewrite cosine technically to the 1. I'll write it in just to remind you. And then I need to take the derivative of cosine, which is negative sine. Okay. Then have the derivative of cosine at the end. And what's the derivative of the cosine by itself at the end? Also negative sine, and it's already negative here, so it'll become positive sine x at the end. Yeah. Is everybody good with that? Okay. I'm going to take a step just to kind of mush things together, clean them up a little bit, just by moving that negative. It'll help. So I've got really -2 sine x cosine x. I kind of like writing sines first. I don't know why. Plus the sine of x. And it just doesn't have to be written in that order, but that's what I have. Okay, I took a derivative. What do I do after I take the derivatives?
Set it equal to 0?
Yes, sir. To set it equal to 0. Now, this is a trig function. Okay? So it's not like algebra. It's not algebra. It's trig. I can't just move things around, get x all by itself. It doesn't work like that. The thing about this one, though, too, so we're thinking unit circle things here eventually. But the thing about this, too, is that I have 2 trig functions. And what I don't want to do is sort of like separate them on either side of the equation and divide by trig functions. You lose solutions when you do that. It's just like what happens with algebra. You don't want to separate the x's on 2 sides of the equations and divide by variables. So as long as you have variables inside of your quantities, whether it's in algebra or in trig, they all stay together on the same side. And we look to see if they can be factored. Okay? So taking a look at these trig functions that are separated with addition or subtraction, depending on your perspective. What can I factor out of them? Sine x. So the first thing to do is to factor out sine of x, which leaves me with -2 cosine of x plus 1. Okay. Is that good? Yeah? Okay. So that's good. It's a good step. Actually, it gets us to a point where we get to a lot of the times when we factor in algebra. Now that each of the parentheses themselves are separated like this, I set each of them individually equal to 0. So I say, okay, now I have sine of x, and I can make it equal 0. And I have 2 cosine of x plus 1, and it can equal 0. Problem? You guys solve stuff like this in trig. I know you did. So the first one, sine of x is equal to 0. That one's pretty clean already. I don't need to shift or move anything around, but I can think about unit circle stuff with sine. So thinking about your graph of sine of x on the interval, one unit circle interval 0 to 2 pi, where does sine equal 0? You're thinking about cosine. You're thinking about cosine, which we'll actually get to in just a second. What was? 0, pi, and 2 pi. And since 0 and 2 pi are our interval endpoints, I don't necessarily need to write them, but if I do, it's okay. So 0, pi, and 2 pi. So those are the ones for sine. On the other piece that's set equal to 0, we're going to shift it around until we get to the point where it just says the trig function equals 0, equals something, some number instead. So we'll move the 1 to the other side, making it a -1. So this is -2 cosine of x equals -1. And then we'll divide by the -2. So cosine of x is equal to 1/2. Okay? So everybody good with that? A little bit of algebra in the middle of it. All right, unit circle, but now we're not thinking about sine, we're thinking about cosine. Where does cosine equal to 1/2? Yep, it's pi over 3. That's one spot. There's one more. Yeah. And those things that are equal to non-zero values take a lot more work on our brains. They do on mine too, in fact. So referencing your unit circle might be a good spot if you're struggling with those values. All right, so I have an interval. A little bit different than the last interval because it can't actually go beyond 0 or 2 pi. Right, because the way the problem was set up. So I don't need to worry about what happens before 0 or after 2 pi. It's just between them. I have 3 values. I have pi. I have pi over 3 and I have 5 pi over 3. So I need to put them in order. It's really important. Otherwise, you're really going to have some problems. So here's pi over 3. Here's pi. And here's 5 pi over 3. Grab a calculator. This can be very messy. I mean, you can use trig, in the sense of like a unit circle to evaluate these, and that's wonderful if you want to go that route. But the reality is you can use your calculator too. So Katie's got mine, so you guys are going to have to tell me what's going on as we look at these values. You can keep it. I'll let you use it, because that way you can help out with everything else too. All right, so we need values in between these. So let me tell you kind of how to think about this if you're wanting to use your calculator to help you do that instead of working with a unit circle. So I've got 0 and I've got pi over 3, but pi is about 3.14, right? Right? Shake your head, yeah, absolutely. All right, so if I have 3.14 over 3, you're looking at a value that's about 1, agreed? A little bit more than 1, in fact. In fact, since it's a little bit more than 1, that means that 1 is in between 0 and pi over 3. So 1, as an entering value into your calculator, is a really nice one. So let's identify first what values we're going to put in. 1. 1's between 0 and pi over 3. I know it doesn't look like a trig radian value. It is. Like it's a radian value. That's fine. It's not a unit circle, but if your calculator's doing the work for you anyway, it doesn't really matter if it's on the unit circle, right? All right. So I've got a number that's about a little bit more than 1, and I know that pi is a little bit more than 3. So what's a number that's a little bit between 1 and 3? 2. 2 is so nice, so we can use a 2. 2 is wonderful in between here. Okay, so again, pi is about 3. Somebody grab your calc. Tell me real quick. What's 5 pi over 3 with a couple decimals? 5.23. 5.23. So 4 would be a good one. You bet. Do you guys see what I'm doing? We're just picking nice whole number values to plug in. Something that's going to be easy for evaluation and for your calculating way. Okay, so you guys said, or Jeffrey said, that this is like about 5 point something, right? I know that 2 pi is 6.28-ish, right? So 6 would be fine. So these are very nice values for entry purposes into your calculator. So take your calculator then and go into y equals. And remember, you're wanting to know what happens in the derivative, not the original function. So you need one of these versions of your derivative. The one that I probably would choose if it were me picking is I would probably choose this one. Oops, that's really thick. This one that we cleaned up a little bit because it's just going to be easier to type in. So I would probably type in -2 sine x cosine x plus sine x into y1. Please make sure that your calculator's in radian mode. I know I've said it before, but I know also sometimes you guys share calculators with somebody in different math classes, and they might be working in degrees, especially if they're in a trig class. Make sure you're working in radians on your calculator. And you're actually going to plug that value in. So this is f prime of x, so notation-wise, I'm going to keep using that. You're going to plug into y1, not into y1, excuse me, but into your table. That's what I'd do, is I'd go into my table and I'd plug in 1. And then I'd plug in 2. And then I'd evaluate at 4. And then I'd evaluate at 6. And again, I don't care what the numbers are. They're going to be ugly. I don't care at all. All I care is, do I get positives or negatives? So let's see how in sync you guys are with one another. What did you get on 1? Positive or negative? I think I hear everybody saying negative. How about 2? Positive? What did I do?
You said in sync, and so I said bye.
Oh, I see. Very good. Yes. How about 4? Negative. And 6? Okay, did everybody get those same things? Okay, then I'm going to assume that you did it all right because you're all getting the same thing. That's really good. The question was about increasing and decreasing, right? So I'm going to go back up to my number line, and I'm just going to write them in. It's negative, positive, negative, positive. And remember, we're using the interval endpoints as our reference points, not the 2s and 3s, and not the numbers that we actually put in, okay? So where is it increasing? Where is it decreasing? Let me shrink this. Okay, so where is my graph increasing? Okay, so from pi over 3 to pi, open intervals, right? And then where else? Because there's one more positive, right? 5 pi over 3 to 2 pi. And then where is it decreasing?
0 to pi over 3.
And pi to 5 pi over 3? All right. So we will finish up on this lesson next time. Homework would be great for you to start working on it so you don't have as much to do over a fall break. I mean, that would be nice. But it's not due next class period. It won't be due till the Monday after fall break. Office hours today. We'll start just a little bit late. I'll be there by 12:15. My student teacher and I had issues last week and didn't get to meet, so I'm going to visit her class period in the 11 o'clock-ish hour. So I'll be back by 12:15 for office hours if you're doing gateways. Gateway deadline is Wednesday. The rest of my office hours read this week are like they are in the syllabus. Okay. So I got a bunch of office hours on Tuesday, and then on Wednesday I'll be there from 12 to 1. Okay? So come see me, get those gateways finished up. If you finish them and you finish them well, they're going to boost your grade. That's just the deal. All right? So had somebody finish theirs up the other day, boosted the grade by 5%. Okay? In that particular case, it was a letter grade difference. So come see me, get those finished up.